Good morning, all. First, I want to say thanks to Zach for that great presentation, and happy to follow up on that with explaining some of the long-term impacts of deep sea mining. My name is Bryan O'Malley, and I am a deep sea researcher from Eckerd College and Ecofera in St. Petersburg, Florida. For 10 years, I researched the impacts of the Deepwater Horizon oil spill, and for the past 5, I've been establishing baselines and researching the impacts of deep sea mining in collaboration with grants from the Metals Company, as well as this really cool study that we've been doing recently that I'm about to talk about with the UK government. So I really like to start off my presentations with this view of the Earth. It kind of gives a sense of the scale and the magnitude of the ocean. Usually we see the land side of the globe, and this is just a view of the Pacific, which really is almost half the Earth, and most of the Earth's habitat is abyssal plain, right? 4,000 meters or 3-4 miles deep. And it helps put into context that actually this is one of the largest deposits of critical minerals in the world on more than land combined, especially for these minerals, except for copper. But manganese, nickel, and cobalt, the largest reserves in the world, are in the form of these polymetallic nodules. So what are the motivations for this, right? A lot of people have talked about this before in this, I've seen a lot of in this summit, but the clean energy transition, as well as mineral supply diversity and critical mineral independence geopolitically. But why aren't we doing this today? What are the barriers? What's stopping us from this? It's really the uncertainties, right? What are the impacts of deep sea mining? So how can we get access to these minerals? It's through management system from an ecosystem approach, as well as adaptive management, which one of these principles emphasizes, establishing baselines of what is in the ecosystem, and then also looking at long-term impact studies, which is exactly what we did, and it leads directly into our recent study that was just published hot off the press last week in Nature, that is titled Long-Term Impact and Biological Recovery in a Deep Sea Mining Track. And we studied the effects of deep sea mining from the USA original 1979 deep sea mining test, because this was actually, the US was a leader in this space back in the 70s, and this was led by AMCO and Lockheed Martin. This was the mining vehicle. These two, you can see, that's the scale of that. That's a person on the left, so this thing is just huge. And it was propelled by these screws that would go through the sediment. And the two kind of pressures of deep sea mining, right, is actually churning through the sediment, collecting the nodules, and then creating a plume as this thing moves, because deep sea sediments are mostly clay, and you worry about potentially clogging gills of fish or feeding apparatuses of corals. And then that's the track that they took. Kind of looks like a bobby pin, and it mined around 8 kilometers. So using the UK research vessel, this was a NERC-funded project, and it was led by the Natural History Museum in London and the National Oceanography Center. And we sent this was all from actually hand-drawn maps from the 70s, because this was before GPS. And so we went to the approximate space, and we sent down our robot submarine and searched the seafloor and actually found the tracks and found that the scars were visible still after 40 years. However, we found a recovery of mobile animals in the track, and what lives down there, it's kind of a sea cucumber's playground. You can see in the furrows that there's collection of mobile animals, and probably because it's deep and it is collecting food. It's a very food-poor environment, like equivalent to a desert. And there's 2 types of habitat, right? There's animals that live in the sediment and ones that live on the substrate, on the nodules. We found that the nodule fauna were still absent, but that's because the nodules have been collected, so obviously they wouldn't be there still, and nodules take millions of years to form. However, we found that the fauna that live in the mud had recovered. And interestingly, we found that on nodules left behind in the mining track that animals were still on them. And this provides a colonization substrate, which is really important for management, right? If you leave a certain percentage of nodules behind, you can actually promote recolonization. And then maybe most importantly is the sediment plume, right? We actually didn't find any long-term impacts from the sediment plume. Over 40 years, this had completely recovered. So this constrains the zone of impact to just the track and just the nodule fauna, the ones that rely on nodules in the track. So once again, leaving behind a certain, maybe 10% or so of nodules can be positive for promoting recolonization. And some takeaways from this is that really this presents a major advancement in deep sea mining research. This provides actionable insights for deep sea mining management, for example, like minimizing the collector footprint or new technologies in collector development, as well as leaving a certain percentage of nodules behind, and then highlights the next area of focus that research should be on, and that's cumulative impacts and a commercial scale mine, right? Because this was just a small mining test. So, yeah, and with that, I'd like to acknowledge the team that helped on this and was the co-authors of the paper. And my contact information's here, and you can access the paper through this QR code, or feel free to talk to me after, and I'll send it to you guys. But yeah, appreciate it, y'all.